When we think of describing points on a plane, oftentimes we think of the rectangular coordinate system, where we have a point maybe like right here on this circle, and we talk about, okay, how do I describe that point? Well, I go over x amount and then up y amount, and we have a point up here, x and y. Now, that serves us very well. The rectangular coordinate system, you know, we go over so much on the x and so much up on the y. That serves us very well, but you got to admit it's a little bit unnatural if you're dealing with points on a circle. I mean, a rectangle and a circle, they're different. So maybe instead of describing the point by this rectangular system, maybe another system would serve us better. Now, when we're dealing with two dimensions, like x and y, we deal with polar. In other words, what we do is we take the x and the y and we write it in terms of polar coordinates. Now, when I say polar coordinates, what I'm talking about is r and theta. And here's what that means. Notice I've drawn a circle here. I've got this point on the circle, and I've got the terminal side right here of an angle. I rotate this amount counterclockwise, and then I go out r from the pole right here at the center, or the origin on this thing, the xy axis, and we go out here to hit the circle. So I can describe this point by the degree or the radian of the rotation, the angle of the rotation, and then how far out I go to that point. So what we've got to do is we've got to figure out, well, how do we go from x and y to r and theta? In other words, we want to see what the relationship is. Well, one of the things that we can notice right away is that x squared plus y squared equals r squared. So that's right away, the Pythagorean theorem gives us that. And now, if we want to talk about the angle, theta, well, you realize that the tangent of theta is equal to y over x. So we can use that, maybe say, okay, theta is equal to inverse tangent of y over x. And we can get the theta. Now, this won't always give us the angle that we're looking for, depending on which quadrant it is, but we'll talk about that more in a minute. But this is the relationship. So we've got x and y, and we want r and theta. Well, r can be gained from calculating the x squared plus the y squared and take the square root of that. That will give you r, and then we can get inverse tangent. So, for example, let's just, and we'll look at some more relationships here in a minute. But let's suppose that we have a point right here, and let's suppose it's the square root of 2, comma, the square root of 2. And we've got some angle down here. Don't know what it is. And let's suppose, so here's the square root of 2, and here's the square root of 2. So we go over square root of 2 and up square root of 2, and we get this. Okay, right now we have a rectangular point. That's a rectangular coordinates. I want to write the equivalent polar form. So here's what I need. I need an r. R squared is going to equal the square root of 2 squared plus the square root of 2 squared. So that means that r squared equals 2 plus 2. That means that r is equal to the square root of 4. Now, we're not going to do plus or minus the square root of 4. We're looking for a length here, so it's just going to be positive. So right away, we have 2. So here's what we have. We have square root of 2, square root of 2, and what we want to do is we want to write it as terms of r theta. So I've got a 2 right here. Now what I need is the theta. Well, I know that tangent theta is equal to the square root of 2 over the square root of 2. Opposite over adjacent. That's 1, of course. So we've got tangent theta equals 1. Now I say theta is equal to inverse tangent of 1, which is equal to pi over 4. So now we have the equivalent polar form of the square root of 2, square root of 2, we have 2 pi over 4. Now, we have to be a little bit careful because let's suppose instead of that angle, let's suppose we have this. Let's suppose that we have this point. Okay, so here's my theta, and this point up here is negative square root of 2, square root of 2. And we want to describe that point. Well, here's what we do. R is going to be the same. R is 2. And now I'm going to just go in here and say, okay, tan theta equals square root of 2 over negative square root of 2. I just blindly do that. And what I get is tangent theta equals negative 1. Well, now note that if you do inverse tangent of negative 1, you don't get this angle right here. You're not going to get that. What you're going to get is negative pi over 4. That's clearly not the angle that we're in search of. That's an angle in quadrant 4. That's going to happen. So when that happens, you can remedy that by just saying, okay, theta is in fact negative pi over 4 plus pi. Just add pi to it, and that will fix the problem. Every time your point is either in quadrant 2 or quadrant 3, and you do inverse tangents, you're going to need to add pi to it. And the reason for that is inverse tangent will always output angles that are in between negative pi over 2 and pi over 2. They're never going to give you, it's never going to give you anything outside that range. So this would be 3 pi over 4. So in this case, we've got negative square root of 2, square root of 2, and in polar form that would be 2 and 3 pi over 4. Now this is just meant to be a quick review of polar because what we're really getting ready to talk about is cylindrical coordinates. Now one other thing that we need to take note of is this, that this x and y here, if there are other relationships that we've not taken note of. One is, notice that if we take the sine of theta, that's equal to y over r. And that means that y equals r sine theta. And also, we know that cosine theta is equal to x over r, which means that x is equal to r cosine theta. So these are relationships that we need to be aware of when we're trying to convert back and forth between rectangular and polar. So let's summarize here. We've got x squared plus y squared equals r squared. We know that theta is equal to inverse tangent of y over x, or theta is equal to inverse tangent of y over x plus pi. One of those two. So that's a couple of relationships that we looked at. We also know that x is equal to r cosine theta, and y is equal to r sine theta. Now, these two things will help us to go from polar to rectangular. So let's just suppose that we've got this situation. Let's suppose that we've got 3 comma pi over 6. And we want to figure out what that is in rectangular. So now we're going from polar to rectangular. We went the other way, now we're going back. Okay, so first of all, what we need is an x. Well, x is equal to 3 cosine pi over 6. And y is equal to 3 sine pi over 6. Okay, so let's see what this is. 3 cosine pi over 6, well, that's 3 times the square root of 3 over 2, which is 3 square roots of 3 over 2. That's the x. The y is 3 times 1/2, so that's 3/2. So there we have it. We have 3 square roots of 3 over 2 and 3/2. And that gives us our going from polar to rectangular. Okay, so that was just a quick review of polar. Now, we want to talk about cylindrical. When we talk about cylindrical, realize we've got rectangular, and we'll talk about the 3 dimensions. Okay, in 3 space, you've got x, y, and a z. So we haven't talked about that yet. Well, when we're dealing with 3 space, polar doesn't do the job, right? It gives us the r and the theta, but we need a little more than that. So what we need is we need r, theta, and then we need to put in the z as well. So with rectangular, we have x, y, and z, and with cylindrical, we have r, theta, and z. And of course, z is equal to z. So that's the other relationship that we need to be aware of, that z is equal to z. So now, for example, let's look at this. Let's suppose that we have this situation. Let's suppose that we have the square root, or let's do this. Let's suppose I have the square root of 3. Let's suppose I have 1, and let's suppose I have 4. Now this is rectangular. Okay, this is rectangular coordinates. And what I want is I want an r, theta, and a z. Well, the easiest thing you can do is put in the z. We know what the z is. The z is 4. That's super easy. Then everything is back like polar. Everything is just back exactly like polar. So we've got r squared is equal to the square root of 3 squared plus 1 squared. And that will give us r squared is equal to 4, which means that r is equal to 2. And then we can go ahead and say and look and see, well, as far as the theta goes, we know that it's going to be inverse tangent of 1 over the square root of 3. Now, 1 over the square root of 3, I guess that's going to be pi over 6. Because remember, on the unit circle, the y is 1/2, the x is square root of 3 over 2, so 1 over, so it's going to be pi over 6. And there we've converted. So the only additional thing that you do with cylindrical is take into consideration the z. And that's it. Now, we want to consider what a graph would look like if we're dealing with cylindrical coordinates. For example, if you look at this, theta equals pi over 4. Now, if we were in polar, if we were just dealing with polar and there were no z and we were just on the plane, the x and the y, 2 dimensions, this would just be a line. And in fact, if we were dealing with polar, we would say this. We would say, well, I know that tangent theta is y over x, and theta is pi over 4, so we would have tangent pi over 4 equals y over x. Well, tangent of pi over 4 is square root of 2 over 2. Well, it's 1. It's 1, isn't it? Okay, it's square root of 2 over 2 divided by the square root of, no, it's 1. What am I talking about? So 1 equals y over x. So this would just be y equals x. So if we were dealing with polar and no z, then this would just be a line. In other words, theta would be fixed at pi over 4, and then the r would take on every value. So you fix theta, and then r just runs rampant. No matter what r is, theta is pi over 4, so what you get is a line, y equals x. But we do have the z coordinate. So now what we have is, we have the r is running rampant. It can be anything. And also the z can be anything. So when you take both of those into consideration, what you have is a plane. Like this. A nice plane. And notice here you've got the pi over 4, and the plane just runs. As long as you keep theta pi over 4, r and z take on all values. So you get a plane. It's like the line that's just been extended. Now it goes up on the z-axis and down. So that's a surface with cylindrical coordinates. Now let's look at this one. Here we've got r squared plus z squared equals 9. Now, sometimes when we're trying to figure out what something looks like, it might help us if we see something obvious that we can convert. It might help us. For example, I see this r squared and I'm thinking x squared plus y squared. Right? That's what r squared is. And then I've got plus z squared. Now this I can immediately recognize. Okay, so I had trouble with this. So I say, wait a minute, let me put this in something I'm more familiar with, and that is the rectangular. Now I've got x squared plus y squared plus z squared equals 9. Well, that is a sphere of radius 3. So immediately I know how to get the graph of that. I know what that's going to look like. It's a sphere of radius 3. So sometimes that's a technique that you can use. It just takes practice looking at several different equations to see if you can figure out what's going on. Now, let's look at this one, z equals r. Okay. Now, another method for figuring out what something like this looks like, we could do this. We could say, okay, let's suppose that, let's just think about what this looks like by looking at setting values for z. Okay, so for example, let's suppose that z is equal to 1. Okay, let's suppose that z is equal to 1. Then what we have is r is equal to 1. Now that's a circle of radius 1. Okay, that's a circle of radius 1. Now what about if z is equal to 2? Then that's a circle of radius 2. So you can see we've got this situation where as you get higher and higher powers of z, or higher and higher values of z, you get bigger and bigger circles. First you have a circle of radius 1, then a circle of radius 2, a circle of radius 3, and so forth. Okay? And of course, if z is equal to 0, you know, r is equal to 0. So it's like a point, radius 0. So if you think about that, if you visualize that, what you're going to get is a cone. So let's take a look at the cone. Okay, so there's a cone. So these are just some examples of surfaces, and it just takes a lot of practice looking at different surfaces and learning how to reason about whatever equation you've been given.